Right, good morning. Thank you very much for holding out. In case you haven't looked at the news, we have an election yesterday in the US and it doesn't look good, but let's not get too depressed about it. Okay, so what we have done in these lectures after some basic introduction to what GAP does and how it is used is we started with the orbit algorithm. From the orbit algorithm, we got to stabilizer chains, and stabilizer chains for permutation groups gave us a way to calculate a composition series, a composition tree. For matrix groups using constructive recognition, we also have seen ideas how one can build a composition tree. But of course, if you come as a user to the system, you typically don't come because you want a composition tree. You want something else. And therefore, I want to talk about the method which is used for more structural computations. This is called the solvable radical or the trivial fitting method, which has been developed over the last 15 to 20 years, mainly by Derek Holt, John Cannon, and I have also contributed a bit there. So, yeah, that's the fifth chapter about structural computation. So, let's start with some arbitrary finite group. What I take is initially the radical, the solvable radical, the largest solvable normal subgroup. If you have two solvable normal subgroups, it's not hard to see that's a basic exercise once you have the isomorphism theorems that they together generate a solvable normal subgroup. So I take the solvable radical, then the factor group cannot have any solvable normal subgroups. Why? Because if there was a solvable normal subgroup, solvable unsolvable implies solvable, which would contradict maximality. So this factor cannot have any solvable normal subgroups. That means the SOCL, the minimal normal subgroups, all must be simple non-abelian. And if we look at simple non-abelian groups, their direct product, we basically can't mix if you have a direct product of cyclic groups of prime order, a vector space. The general linear group as automorphisms of this group can do mixing. Basis vectors are not necessarily mapped just to other basis vectors, but to linear combinations. But for simple non-abelian groups, that cannot happen. So, if I look at the SOCL, S star modulo R is the SOCL of this vector group. The action on the SOCL is permuting the simple SOCL factors. P car is the kernel of this permutation action, and I actually get a homomorphism from the group G in the automorphism group of its SOCL. And if I have just a simple group of one type, the automorphism group of this is automorphism group of this one simple group, wreath S, what the number of factors is. These are groups I can represent nicely. So, this factor group, modulo the radical, has a nice representation. And indeed, there are, for example, theorems which show that if the whole group is a permutation group, this particular factor group can always be represented as a permutation group of a degree which is not larger. But in general, even if the whole group is a matrix group, in general, because the simple groups tend to have permutation representations of a comparatively small degree in relation to their order, this means I could typically represent this factor nicely. And that I already mentioned, basically. Right. The next step is to use the solvable radical. So, the solvable radical is a solvable group, so I can find a sequence of subgroups, each of them normal in the whole group, that each factor, subsequent factor, is elementary abelian. So, the solvable radical is put together from vector spaces. And what I want to do is, I want to calculate well, no, sorry, let me first say, so we have these vector spaces, these vectors. For each of the vector spaces, if I want to do anything with a vector space, I need a basis. And such a basis is basically given by part of a polycyclic generating system. That's exactly the kind of generating systems Heiko talked about. He talked about P groups, but you can do the same thing for solvable groups, and we calculate such a generating system for the radical. And if you worry about working that I will work in factor groups, in fact, I don't need to ever write down other factor groups. I can work with pre-images of subgroups and elements. Okay. So, now how do these algorithms work? These algorithms first work in the factor group G modulo R, using its special structure, using that it is comparatively small in relation to the group. And they then lift the result that they assume, let's assume the result is known modulo R, get a result modulo R1, next get a result modulo R2, modulo R3, and so forth, until we have the result for the whole group. And what we aim to do there is to reduce that calculation to calculations on these vector spaces. And if we do calculations on the vector spaces, we hope to be doing something like linear algebra. Linear algebra is one of the things we can do concretely for calculations. And what I want to show you how this works in some examples. Typically, so to describe what happens, one just needs to describe a single step. So from now on, we will have, I simply assume, have the situation that I have an elementary abelian normal subgroup. I assume some result is known for the factor group, and I want to get that result for the whole group. Well, often some calculations reduce to orbit calculations. And what we can use there is the fact that orbits of a normal subgroup form a block system. So, for example, if I have some group U here, I have the normal subgroup, and I want to calculate the orbit of some point under this group, U. And that point actually could be something complicated. It could be an action on subgroups or on elements of the group or so. The way I can do these orbit calculations is that I first stabilize the block, which is the orbit of the point under N. Once I've stabilized the block, I know that the stabilizer in the subgroup basically needs to complement N in this factor here. And so what I need to do is I first need to calculate stabilizers for this block, and then I just need to correct these stabilizers to get element generators for this subgroup here, and assuming this subgroup is known. And what I do is basically, if I have an element A here, it will map omega to something where already something in N map sits, so I just need to divide off N from A and get an element actually which stabilizes not just the block but the point. So that is something which inherently is used to make orbit calculations more feasible. So let's look at some example, and the first example I want to look at is conjugacy classes of elements. So the group, these are orbits of the group under action on itself by conjugation. For every class, conjugacy class, I want a representative and the centralizer of the representative. So the first thing is I need the radical factor. So how can I get these? These are almost simple groups. I can look them up, for example, in databases like the Web Atlas web pages, and I mean, okay, the computer wouldn't open a wouldn't open a web browser and browse through these web pages, but it would store information which has been taken from the same base as these web pages. So we can look up conjugacy class representatives, or actually in a simple group, even an approach of picking elements randomly and just testing for conjugacy works pretty well. Next, more complicated thing is, let's suppose I have a direct product of simple groups. Well, if I have classes for each of the factors, classes of the direct product are trivial to get. That's just the Cartesian product. So I can write these down. Finally, I have a group which lies between this socle and its automorphism group. And what will happen is that the classes, some of these classes here in the direct product will fuse together under this action by permuting components, and I have external classes which come from the actual outer automorphisms. So there I need to do some further tests, but basically this will get me the conjugacy classes for this factor. So let's assume we have gotten these. And what happens now is the next steps basically mimic what has been done already a long time for solvable groups, and was originally written up in '87 in a paper by Mackey and Neubüser. So let's assume we have an elementary abelian normal subgroup. We know the conjugacy classes of the factor. When two elements G and H are conjugate in G, obviously the corresponding factor group elements are conjugate in the factor group. So every class of the factor group must be the union of images of classes in the group. Let's take one such class representative and its centralizer. Then what I need to know is, how does this coset split up into conjugacy classes? Well, the centralizer acts on elements of this coset by conjugation, which I can split up like this, and I can write in this form. Okay, so what is happening here? The coset representative stays the same, but I can interpret this as a map if I now just look at the n part of such an element in the coset. Right, every coset element is defined uniquely by its n part if once x is fixed. It's a map where n gets mapped to n acted on by C times this commutator. And n is elementary abelian. It's a vector space. So in a vector space, often people like to write it additively and not multiplicatively. When we look at it additively, what does this mean? N conjugate by C now is just a linear action on n. And here, I'm multiplying with an element. Well, additively written, I'm adding an element. And this element does not depend on n. This just depends on C on x. So C acts on n by a linear part and by adding vectors. That's what we call an affine action. So what we simply have is an affine action of the centralizer on n, and we calculate orbits and stabilizers using the fact that n is a normal subgroup, what I had on the previous, on the slide 2 slides ago, and orbits will correspond, orbits and stabilizer will correspond to conjugacy classes. And as I said, yes, the n orbits correspond just to translation. And in fact, I can deal with this by factoring out a subspace. So by calculating these affine orbits, I get conjugacy classes from the factor group to conjugacy classes of the group. Let's look at this in an example. What you can often do in GAP is that you can turn on an info level. It's not always obviously clear how the info class is called. There basically one would need to look in the code, but just to give an example here, I'm picking some transitive group of order of degree 12. So this has a structure of is 2 wreath product with PSL 2, 6. Sorry, this is rubbish. Sorry, L6 is A5. No, that's PSL25, but PSL25 acting on 6 points. That's the action of, you get that action by, again, if you take A6, in A6 you have an A5. A5 is a point stabilizer, fixing one point. But now you take the non-trivial the outer automorphism, which doesn't come from S6. That will map that point stabilizer A5 to a group which doesn't stabilize a point, but happens to be transitive, and that's this group L6. And I need the actual permutation group to describe what the Reith action is. So this is 2 Reith PSL25, and then there is another 2 on top. Okay, so this L6 split 2 is an S5, but acting transitively on 6 points. And I asked for the conjugacy classes. And now, because I turned this info level on, GAP tells me where it is. It starts with it represents the top factor in degree 12, calculates conjugacy classes for L6 split 2, which has 7 classes. And now it goes through, there is a normal subgroup of order 2 to the 6, which is 64. And it goes through all the classes of the factor and splits them up and collects finally 2 classes of the group. And with these classes, yes, I can test whether elements are in classes, I can do conjugacy tests, and so on. Right. Another example, subgroups. So again, I assume N is elementary abelian. How can I find all subgroups or representatives of all subgroups up to conjugacy? Well, let's look at an arbitrary subgroup U. If I take this subgroup, I can look at the group of its image in the factor group, and I can look at its intersection with N. Well, in the factor group, I assume things are known. So I can assume that this group A is already known from the previous step. This intersection is a subspace of a vector space. Well, if we have a vector space, it's not hard to find all the subspaces. That's just enumerating row echelon forms of matrices. Furthermore, this group B is normal in U because it is let me first start. A is generated by N and U because it's the image of U in the factor. B, the intersection, is normal in U as intersection of U with a normal subgroup. But N is abelian, so B is also normal in N. So B is normal in N and U and therefore in A. And therefore I have a factor group situation. I can look at this factor group, and in this factor group, U modulo B is a complement to N modulo B in this factor. And if I want subgroups up to conjugacy, let's assume I have obtained A up to conjugacy. I will then describe the subgroups B only up to conjugacy by the normalizer of A, and then I need to calculate these complements. Yeah, so what I do in the algorithm, I assume all the A's are known from a previous step. I calculate the B's. I calculate complements. Complements are up to conjugacy in A, but I want conjugacy by the normalizer of, let me first say, I need to how do I find these complements? That is basically calculation of a one cohomology group. And cohomology really is just the posh cousin of linear algebra. That's a linear algebra calculation with some action. And finally, I need to fuse these complements under the action of the normalizer of A and B, because there could be some further of them could be conjugate there, and normally cohomology just gives me conjugacy up to N, or up to A. Okay, so that gives me conjugacy classes. Let's look again as an example. Let's take SL25 as a small example of a subgroup which has an elementary abelian normal subgroup. I make a permutation group out of it. And now I form the Reith product with S3 in its action on 3 points. So what this will give me is a group which now has not a single 2 on the bottom, but a 2 to the, because I take 3 copies, it has a 2 to the 3 on the bottom, then has 3 copies of A5, and then on top has an S3. And I asked for it, and that's already quite a sizable group. And I asked for conjugacy classes of its subgroups. Well, it starts, it finds there is an A5 in the socle and found the isomorphism type. Again, it looks in a library, and that is nominally the library of tables of marks. Tables of marks are a way of compactly storing certain information about the lattice of subgroups, but in particular in GAP, what this library stores as well is essentially generators for subgroups representatives. So we get the subgroups simply from pre-computed information, pre-stored information. Then we take the 3 copies of A5, but that's just a direct product. And subgroups of this direct product we can construct as subdirect products. I'll talk about this in a moment. I need to extend these because there is the S3 on top. They could get larger. So in this 3 copies of A5, I get in total 1,995 subgroups. Why does it say overall that many? Because there are some of them are conjugate now under the action of S3. And then finally, I have this normal subgroup of size 8. I run for each A, I run through all the possible B's. Well, there aren't that many subspaces of the vector space of size 8. And I'm leaving out some of the calculation. It gets the other subgroups, and in the end, it finds this group has about 5,356 subgroups. Yeah, so that gets us subgroups, and in principle, these calculations should not just work for permutation groups, but but also for matrix groups. It's just if you want to do this for matrix groups, it's currently not built in by default, but you would need to load a package which is called matgrp. The only caveat is that requires some other packages which require compilation, so this will not necessarily, no, it will actually, because they're included in Windows, it will run under Windows as well, but under Unix you need to do some extra compilation. It's a little bit fiddly to install. But with that, subgroups, maximal subgroups, conjugacy classes of elements are also doable in matrix groups. Okay, in the last about 25 minutes plus 2 epsilon, I want to talk about a few topics which I could have tried to squeeze in before, but they didn't fit well. But these are topics where I think, or where they were initially a bit too advanced or needed too many things, but topics which I feel will be useful. So, we talked already about in the first lecture, there is read to read in a GAP file and there is print to. What if you have other data you want to transfer in GAP or out of GAP? One thing, if you have data which is in a spreadsheet format, there are functions read CSV and print CSV, which read or print spreadsheets in comma-separated variable format. In some cases, if you're storing information or if you want to get information out of GAP about some calculations you've done, the results, spreadsheets are convenient ways of storing them, and you could read these spreadsheets into Excel or whatever your favorite spreadsheet program is and manipulate them there. Then there are commands which can actually read an arbitrary text file. What you need to do is you need to use input text file, which gives you a stream. Then there are commands read byte or read line. Read line reads the whole line in as a string. You need to close it at the end. And then you get that text file as a list, as a sequence of GAP strings. And you can do things with these GAP strings. They are lists. You can take sublists. You can look for what characters are in there. This you can use if you have files which come from other software in some format which GAP can't read directly. That with this you can write your own routine to read in data. Very convenient if you're interfacing with some other program. Finally, what you can do is gap can call external programs by calling exec, and then comes a string. And that string is basically the call to call the other program. Under Unix or on a Mac, this is simply passed to the Unix shell. So you could say exec ls, exec string ls. ls is the Unix command to list the contents of a directory, or you could do exec cat/etc/passwd and have gap print out the contents of the password file or so. That's incidentally the reason why we don't recommend putting gap on a web server. It's with these functions, it's really, really hard to lock it down that people can't do very nasty things through gap. This also works under Windows, but there it calls what is command com. That's the old text shell under Windows. So it is possible to call commands. I think it should, unless Microsoft changed something in the more recent versions, this should work for the grape package, which works with graphs, to call naughty for graph automorphism calculations. But to do this on your own, if you've never done command line programming in Windows, I don't recommend that you try that. Okay. Next thing, as I promised you in the first lecture, I would talk a little bit more about method selection. So, method selection is the mechanism, or the name we give to the mechanism, which will deal with a situation that you have different algorithms for the same result, but they work only in certain cases. The algorithm for order of a permutation group is different than the algorithm for order of a matrix group, say. And what it will do is, it takes all the methods installed for the same operation, and it tries to select the one which is most specific. So, if you want to see this, you can call trace methods. So, for example, for pseudo-subgroups, actually the operation is pseudo-subgroup op. Why is it different there? Because we cache pseudo-subgroups by primes, but there can be multiple primes, and therefore it needs to hide this second argument behind something. Anyhow, so if I take the symmetric group on 10 points, I ask for a pseudo-subgroup, and if I've turned this tracing on, it tells me, okay, it's a method which has an identification for pseudo-subgroup op, which has an identification string which tells it symmetric. So it's a method for the symmetric group. And what I can actually do, it also tells me this method is in the library in the file gyp_prim_sua group permutation symmetric or alternating. Remember, I told you we were initially limited with the 8+3 characters in line 1567. So you can go in this lib directory, open that file, and look explicitly at that method and see what it does. Well, and then it does the calculation. And well, if you look at this method, what you see is for the symmetric group, we just write down the pseudo-subgroup. It's not very hard. This is an easy well, to work it out in detail is a little bit calculation, but it's you might have seen this once you know what wreath products are. It's not hard to describe the pseudo-subgroups of the symmetric group. If you want to see in more detail how gap comes to this method, there is actually a gap level function which is called applicable method. So this function, when you call it, returns the gap function which is called to execute that method. So it gets as arguments the name of the operation, the R list of arguments on which this operation is called, and a print level. The print level, the higher the print level is, the more information you get. So let's look at this in this case. Pseudo-subgroup op is the operation which is called. We call it with two arguments, the argument G and the number 2, and I set the print level to 2. Okay, now it goes through and it tells me what gap actually does. The highest ranked method, the most specific method, is a pseudo subgroup for the natural, for GL in its natural representation. Why is it higher ranked? Because in some way matrix group even is considered more special than, or has more implications than permutation group. So what this, well, and this is, I think, even artificially ranked high to be higher than the nice monomorphic. Anyhow, so similarly as for Sn, you can describe what the pseudo subgroups of GL are. You need to distinguish two cases. Is it, say, the defining characteristic or not? But in the defining characteristic, it's upper triangular matrices. If it's not defining characteristic, it's again basically certain Reith products. You can write down what the pseudo subgroup is. But this group, of course, is not GL. So this method is not used, but Gep skips it. The next method offered is the group what we call handled by a nice monomorphism. I told you that currently a lot of methods, for example, for matrix groups, for automorphism groups, implicitly use an isomorphism to a permutation group. We call this a nice monomorphism, nice because it goes in a group where calculations are nicer, not because it's otherwise particularly well behaved and reads all the answers. But and the group is not of that property, so we are also skipping it. Okay, next comes for groups which are solvable and know a polycyclic generating system in the sense as Heiko talked about. This group is not solvable. So we're skipping this, and then comes this method which is labeled as symmetric. An applicable method returns a Gep function, and I could type print of ME that will print me this Gep function, and I can see within Gep what kind of code is called. If I set the print level even higher than 2, if I set it to 1, it doesn't tell me the methods it skipped. If I set the print level higher, it starts telling me why these methods were skipped, what conditions these methods required and were not satisfied by my arguments. And these can be conditions. In this case, these are basically just conditions on the first argument on the group. But it could be conditions on all the arguments. So if for some reason you would define something which are pseudo subgroups for negative integers, you could install a method which would allow you to calculate these however they are defined. Okay. There is one further thing which method selection can do, and that's the effect of the method going, yes, yes, I know, please, please pick me. And Gep picks the method, and the method looks at the problem and says, no, thank you, not me. Why do you want to allow this? You want to allow this because method selection does not force a test of properties. That's very important. We don't want the system to start running away and pretend it's intelligent. That can go badly wrong. So, if you have a method which requires a group to be solvable, the method selection will not do a solvability test if you don't know it. But as author of this method, you might know that you say, well, if the group is solvable, this method is so much better than anything else that it's worth to do a solvability test. So you will install this method without requiring solvability. You will give this method a higher rank. I'll get to that in a moment, so that it gets picked early on. You do the solvability test in your method, and if the group is not solvable, you say, okay, go on, no, sorry, I jumped in the queue, don't take me, go the normal way. And you do this in your method by calling try next method. And in applicable method, you can give an extra fourth parameter, and this fourth parameter tells you the method. Then it will not give you the first applicable method, but the kth applicable method. So this parameter being 1 is the same as if it's not there. But so here, let's call the same thing and pick the third applicable method. What happens is Then the one I had before gets skipped. There is a method in between for alternating groups, which is not applicable. Then the second one is a method pseudo-subgroup for permutation groups, but because of the 3, it's also picking this. And then it goes into a very generic method, which just needs that we have a group and a prime. Well, this would not happen in real life because the symmetric group methods doesn't bail out, but sometimes it's interesting if you want to compare how things to behave. This allows you to get the actual function back, and you could call this function ME or whatever you call it on GN2 to calculate it if, say, you don't trust a particular method. Okay, how do these methods actually get into the program? They do so with the command install method. Install method gets an operation for which it is to be installed. For example, order. For example, pseudo-subgroup op. For example, normalizer. For example, conjugacy classes subgroups. Next, and you will see a lot of these install methods in the library. If you look through the library files, that's basically what they do. Next comes an identification string. This is the string which trace method or applicable method print out to identify these methods. Then, well, let's skip this for a moment, comes a property list. The property list is just a list of conditions. Say the method for pseudo-subgroup for permutation groups. The list, each condition is for each of the arguments. We want the first argument to be a permutation group, the second argument to be a positive integer. These arguments also are used to calculate the value, the basic value of the method. So I said the most specific, what it actually does internally, depending on how much is, what conditions are there and what they internally imply, a numeric value is calculated. And on the previous slides, actually, these numbers here were the numeric values of these methods. And that is used for ordering the methods to decide which one to try first. Okay, there is this family attribute which looks a little bit weird. You could just type true. The reason this is there to basically check whether elements fit together. So just to give you an example where you would want to use it. Suppose you have a polynomial over GF3 and a polynomial over GF5. These polynomials might have exactly the same kinds of properties. They're polynomials, they're stored by coefficient lists, they're polynomials over a finite field, but you can't add them because they're in different characteristics. And so every object in GAP also points to something which is called a family, which would be in this case, say, characteristic 3 or characteristic 5, and would do this. If you look in the library, you will often see that there is something like is calls elms. This would say if you have a group and elements that the element actually fits to the group, that you don't call it for a finitely presented group and a permutation or so. Easiest to see this is probably by looking in the library. Then comes an offset. You can deliberately move a method higher. This is because this automatic ranking will never work perfectly. And then comes a gap level function, just an ordinary gap function with as many arguments as you specified here in this property list. And that's the function which actually does the calculation. There also is, and you will see this in the library, sometimes install other method. That's because these operations initially get declared for certain parts of arguments, and sometimes you want to call it with slightly different arguments or a different number of arguments than declared. Okay. You can create your own objects, and for that you would need the method selection. This is not something to read through in detail. This is just a very basic template, and I'll put this on the web pages where you could look through and get, if you were interested in creating your own objects. So, What you need to do, you need to have a category for your objects, you need to create a family where your objects are in, and a representation which have your objects. Category is mathematical properties, representation is the way how is it stored. You make a function for creating your objects and you create them with Objectify. You need to have a function for a method for printing your objects. So GEP actually will know what to do when to output. And the way I create these objects is basically is positional object rep is a list which is packed into nice paper to look nicer, but just has two parts, part component 1 and 2 in my cases. And that's how I'm creating these objects from a list from two part arguments. In this case, I install a method for 1, for multiplication, and for inverse. So these are pairs of objects which say would be a group. And I define some kind of multiplication. I don't remember what this actually models. It's some multiplication. That's how you can make your own group. If you have objects with some weird multiplication, you can make a group of them. You also need to define an equality method and a smaller comparison. This is because sets use sorting in between. And with these things, you could create your own objects, do division, multiplication, powering. You could create a group of these objects. You get a warning because they are your own objects and GEP doesn't know by default whether they would multiply associatively. You can calculate the group, the size of a group. You can make an isomorphism to a polycyclic group and get its elements. So if you have your own objects, you can make groups from them and use GEP's mechanism for working with these groups. Well, one task which is surprisingly useful is running through tuples of elements. So we had conjugacy classes of elements, but sometimes you don't just want conjugacy classes of elements, but of lists of elements or lists of objects. A, B, C, lists A, B, C. How can you do this up to conjugacy? Well, if you have lists, if you don't swap the ordering, you enumerate the possible first entries up to G conjugacy. Then you take the centralizer of the first entry and enumerate the possible second entries up to conjugacy by this centralizer. And that corresponds to double cosets. The classes, if we had full conjugacy, it would be cosets of the stabilizer, but because we have conjugacy only under a subgroup, we get double cosets. That's what is used by G quotient by some of the isomorphism search as internal mechanism. G quotient simply runs through tuples of elements and looks, can I map the free generators to these elements and have it satisfy the relators? So, for example, to do this, let's say I want subgroups of F7 generated by a triple 2 cycle and a 4 cycle. A is this element, B is the 4 cycle. I take the centralizer of the 4 cycle, I calculate the double cosets, and by conjugating and all of these tuples, since I can always conjugate any double 3 cycle to this particular double 3 cycle, I just need to take this double 3 cycle and conjugates of this with representatives of the double coset and then get the subgroups. Some of these subgroups happen to be conjugate still. Why? Because that conjugation happens under things which would not fix map the generating systems. Such a group might contain other elements of this type. Okay. This is a special case of a more general process when you construct combinatorial objects. Often you construct combinatorial objects, you construct them in parts that you have two parts that you put them together, and these two parts somehow intersect. What you do is you construct the parts up to the appropriate symmetries, and then you need to look at how can you put them together up to symmetries which fix each of these parts, and that again is double cosets. Now double cosets under the potential full group of symmetries, but cosets modulo symmetries fixing omega and symmetries fixing delta. And one example where this happens is, for example, if we want to construct intransitive groups. If a group is intransitive on two orbits, we can look at the projections onto both orbits, look at the images up to conjugacy. Then if we map one kernel, each kernel of the projections to the other image, we get normal subgroups D and E in the images, and the factor groups are isomorphic. That's what a subdirect product is. And so what we need to do to describe these groups is we need to find, if we have A and B given, and if we want intransitive groups, we need to look at all possibilities of A and B, look at possible normal subgroups D and E in both groups such that the factor groups are isomorphic, and look at these isomorphisms up to automorphism induced by normalizer of A and normalizer of B. Yeah, so that gives us these groups. It does not deal with the issue of swapping components. So again, there are some conjugacy tests which would be necessary. But so to construct the groups is I select all possible A's, all possible B's up to conjugacy in the appropriate symmetric group. I select D up to conjugacy by the normalizer of A, E up to conjugacy by the normalizer of B. Check are the factor groups isomorphic, and need to look at the isomorphisms up to double cosets in the automorphism group of this factor. Yeah, swapping is not included there. Let me finish with an example how one would do this actually in GAP. And I will see this is a file. I will put that file also on the web pages together with the slides. Intransitive groups with for a given A and a given B to get all, you would run through A and B. We form the symmetric groups, normalizers in their direct product of these two groups, and we embed A and B. We calculate subgroups, subgroup orbits and normalizers is a convenient function to get subgroup representatives under action of a group. We take the factor group by using natural homomorphism for normal subgroups. That gives us the possible D's. Similarly, we get the possible E's in the same way. We look, are the factor groups isomorphic? If the isomorphism doesn't fail, they are isomorphic. And then I'm running through the double coset in, well, I go to the image of the automorphism group as permutation group and put these generators together and construct the subgroup. And yeah, what am I doing here? So I'm constructing two subgroups. This just looks so horrible because I take normalizer-induced automorphisms of the factor group, translate this to the permutation image of the automorphism group, and do this twice for both parts. And then I take for all the double cosets representatives, I run through all of these double cosets, take the representative, go back under the homomorphism to the automorphism, multiply it with the isomorphism. That gives me the possible maps. And then I'm constructing the product from these elements and collect them together. So that would be a way for constructing intransitive groups. And that is really a model which one can use for constructing in arbitrary situations, groups which are put together in some way. So just as an example, this here we could call this for S4 and S3, and we will get, there are three possible intransitive groups of degree 4 plus 3, which is 7, which have a projection to S4 and S3, namely S4 itself, right? S4 has a factor group isomorphic to S3, so I can glue them together completely. It's not S4 as a permutation group, but it's isomorphic to S4. I have a direct product, obviously, and there is another that's the one interesting subdirect product where the common factor of order 2 is put together. And I could even do this by running through all transitive groups and do this. Okay, right, that's all I have had. Thank you very much for your patience.